This is example 6 with related rates. So again, if you want a copy of this worksheet, check the video description and you'll find a link to a place you can go to download this. You can save it if you want, and then you can print it and follow along with the video if you like. So anyway, example 6, an upside down conical tank full of water has a base radius of 5 feet and a height of 7 feet. And the water is being drained into a cylindrical tank with radius 5 feet and height 6 feet. The radius of the water in the conical tank is decreasing at a rate of 2 feet per minute. And we want to know at what rate does the water level in the cylindrical tank rise when the water level in the conical tank is 3 feet. All right. So we got a lot of stuff going on here. So let's zoom out a bit. Now we go back to our general process here. Step 1, draw and label a picture. So that's really going to help in this case. This is pretty much going to be impossible without a picture. But what do we have? We have an upside down conical tank full of water, and it's draining into a cylindrical tank. So let's go ahead and draw that. Upside down conical tank, and then it's draining into a cylindrical tank. Alright, so here's our cylindrical tank, and then here's the conical tank up here. So in the conical tank we have some water, alright, and then that water is being drained into this cylindrical tank here, so we'll draw some water in here also. Alright, so we have 2 different water levels here. So now let's label a bunch of stuff. An upside down conical tank full of water has a base radius of 5 feet. So base radius, that means this radius up here. And it's a base in quotation marks because, you know, it's upside down, but that's still kind of the base, so to speak. But anyway, that's 5 feet. 5 feet there. And then the height of that tank is 7 feet. So this the height of this entire thing is going to be 7 feet. Alright, and now we have water in here, so there's a water level associated with this. So the water level we'll call H sub 1. Okay, not just H, but H sub 1, because we have a separate water level in here, which we'll call H sub 2. Okay, we have 2 different tanks with 2 different water levels. So for this, for the cone it'll be H sub 1, and for the cylinder it's H sub 2. Okay, and also, zoom in a bit here. This water in the conical tank has a radius which we'll call R. Alright. And if we go down here, what are we told? The radius of the cylindrical tank, here. Water is being drained into a cylindrical tank with radius 5 feet and height 6 feet. So the radius of the cylindrical tank is 5 feet. Okay, just like the conical tank, base radius. And then the height is 6 feet. Okay, so that's the picture there. Now, just like in example 5, you know, we took a 2-dimensional cross-section, or like a 2-dimensional slice here. So imagine taking a 2-dimensional slice of this, and then what are we going to have? Well, you know, here, this is going to be a right angle here, right? If we extend this height here. But, you know, if we take a little 2-dimensional slice, then what we're going to have is a setup with similar right triangles, just like in example 5. Alright, so now let's go ahead and label this. So this is going to be H1 here. So here's H1. And then this entire thing here is going to be 7 feet. So we'll just call it 7. Alright, and then this little distance here is R, and then this was 5. This whole thing is 5 up here. Alright, so that's for the conical tank, but for the cylindrical tank, what if we take a cross-section of that? Well, then we'll have, still has a radius of 5, right? So we'll kind of try and keep it relative to this, to the conical tank. Alright, and then water level here. So this is H2. Okay, that's the height of the water level in the cylindrical tank. So, you know, if we take a cross-section of a cylinder, we're just going to get like this rectangular shape, right? So like here, if we take the cross-section of the cone, we get this triangular shape, triangle. So H2, and then this is 5 right here. So actually the whole way across it's 10, right? But we'll worry about that later if we have to. And then this whole height here is 6. Okay. So now here's the picture of what's happening, and here's our 2-dimensional cross-section. So the cross-section is going to help us with the geometric formulas later. But for now, so that's it for step 1, draw and label a picture. So, you know, there's a lot of information in these pictures, right? So this problem would be very hard, almost impossible really, if we didn't have these pictures. Anyway, step 2, using mathematical notation, make a list of what you are given and what you want to know. So we've skimmed through the problem again real quick. What are we given? Let's see. We're given a bunch of stuff we already labeled, so let's not write it down again. But here, the radius of the water in the conical tank is decreasing at a rate of 2 feet per minute. So if we make a list of what we're given, here we're given the radius of the water in the conical tank is decreasing at a rate of 2 feet per minute. So the radius of the water in the conical tank is r. So it's decreasing at a rate of 2 feet per minute. So dr dt, okay, that's the rate of change of the radius of the water in the conical tank. And it's decreasing, so we have a minus sign, and it's 2 feet per minute. Okay, so again, dr dt is negative because the radius, which is r, is decreasing. So if the radius is decreasing, you know, it's getting smaller, so its rate of change would be negative. So it's negative 2 feet per minute here. And that's pretty much all we're given. You know, everything else we were given, we already labeled here, so we won't write it again. But what do we want? So what we want to know is at what rate does the water level in the cylindrical tank rise when the water level in the conical tank is 3 feet, right? So we want to know the rate of change of the water level in the cylindrical tank. So the water level in the cylindrical tank, that's H2, and we want to know at what rate is it rising. Okay, so what's the rate of change of H2? So in other words, we want dH2 dt, right? And when do we want it? We want it when the water level in the conical tank is 3 feet. Now the water level in the conical tank, that's H1. Okay, that's the height of water in the conical tank. That's H1. So we want we want dH2 dt when H1 is 3 feet. Okay, we want at what rate does the water level in the cylindrical tank rise? So that's dH2 dt when the water level in the conical tank, that's H1, is 3 feet. So that's what we want. All right. So now that's it for step 2. Using mathematical notation, make a list of what you were given and what you want to know. Now step 3, write down the relevant equations. And again, they're probably going to be geometric formulas. So here, we're actually going to have 3 things to write down. So we got a lot going on, right? So, you know, why 3 things? Well, here, just like in example 5, we have similar triangles. So we're going to have an equation from that. And we also have 2 tanks. So we have a volume of the water in this tank and a volume of the water in this tank. So that's 2 equations, plus the similar triangle equation here. So that's 3 equations we're going to have. So let's go ahead and write those all down. So with the similar triangles, what are we going to get there? That equation is going to be H1 divided by 7 equals R divided by 5. Right, so remember, that's just a property of similar triangles from geometry. So H1 over 7, let's separate these a bit. H1 over 7 equals R over 5. All right. So again, H1 over 7 equals R over 5. So that's the similar triangle equation. Now we also have a certain amount of water inside of this conical tank. And then, you know, it's a conical tank, so the water inside of the conical tank is also going to have the shape of a cone, right? And the volume of this water in here is going to be V, and let's call it V sub cone. Okay, because it's the volume in the conical tank. So that's going to be 1/3 pi times r squared h1. Okay, because for the cone, the height is h1, the height of the water. Okay, this represents the volume of the water, not the volume of the entire tank. So V sub cone, okay, for the conical tank is 1/3 pi r squared h1, and it's h1 because that's the height of water in the conical tank, and r is the radius of the water in there. All right, now how about the cylindrical tank? So we'll call it V sub CYL, V sil for cylinder. So the volume of a cylinder is just pi times radius squared times the height. So again, we don't want the volume of the entire tank, just the volume of the water in there. Okay, so the water in there is also a cylinder. So its volume is going to be pi times the radius squared. Okay, so it's pi times 5 squared times the height, which is h2. All right. So why do we say 5 and not r or anything like that? Well, here in the cylindrical tank, no matter how much water is in here, you know, no matter what the height is or whatever, it's always going to have a radius of 5 feet. All right. So you know, when we have any amount of water in here, it's going to have that same radius because it's just a cylinder. It's just got a constant radius of 5 feet. So that's why it's okay to do this here, because that's a constant value. So anyway, when we simplify that, we get 25 pi H2. So that's V-sil. Okay, so here's our three equations, this guy, and that guy. Okay, so now that's it for step 3, write down the relevant equations. And then step 4, implicitly differentiate both sides of the appropriate equation with respect to time. So which one's the appropriate equation? Well, what do we want? We want dH2 dt, all right? So here's H2. H2 doesn't appear anywhere else, so let's go ahead and use this equation here. So let's differentiate both sides with respect to time. So V-sil, if we take a derivative with respect to time, we get dV-sil dt, right, equals, here 25 pi is just a constant multiple, so we still have 25 pi, and then dH2 dt. All right, that's kind of good, right? So here's dH2 dt, that's the thing we're looking for, and we can divide both sides by 25 pi to solve for it. But what about dV-sil dt? What's that? All right, so that's kind of the tricky part here. dV-sil dt, we don't know much about the volume of the water in the cylindrical tank, right? But let's zoom out a bit here and see what we do know. What we do know is that water is draining out of this conical tank and into the cylindrical tank. So the rate of change of the water out of this tank equals the rate of change of water into this tank, right? Because all of the water coming out of here is going directly into here. It's not going anywhere else. It's not, you know, leaking out or anything like that. All the water coming out of here is going directly into here. So the rate of change of water out of here equals the rate of change of water into here, right? So in other words, what we could say is something like dV cone dt equals dV sil dt. But that's not quite right. Okay, there's one tiny little detail on what is it. Well, here, again, just to recap so far, the rate of change of water out of here, dV cone, is the same as the rate of change of water into here, dV sil. But they're not quite exactly the same, equal like this. Why not? Well, here, if water is leaving the conical tank, then dV cone dt is going to be negative, right? Because the water level in here is decreasing. So the amount of water in the conical tank is decreasing, so that means it has a negative rate of change. The volume in here has a negative rate of change. So this is a negative quantity. And at the same time, the amount of water in the cylindrical tank is increasing. Okay, so the volume of water in the cylindrical tank is increasing, so dV sil dt should be positive. Okay, so actually these will have the same absolute value. So if you take the absolute value of both of these, you'll get the same thing. But one is negative and one is positive. So really, to make them actually equal, you just put a negative sign in front of this one. Or really, you can put a negative sign in front of this one if you wanted, as long as you put a negative sign somewhere, because one of the dV cone dt, that's negative because water is leaving the conical tank, right? So the volume of the water in here is decreasing. So this is negative. And then the volume of the water in the cylindrical tank is increasing, okay? So to make this equation true, we have to say this equals negative this. So this is a negative quantity, so it equals negative this positive quantity, all right? So that's what's going on there. Now, how does that help us, though? Well, let's come back up here and say, okay, dV sil dt, let's put the negative over here. So if we leave that as positive, we'll put the negative over here. So actually, it doesn't really matter, I guess, but anyway, let's see what dV cone dt is. dV cone dt, what's that? Well, hold up a sec. So if we differentiate that, what are we going to have? We're going to have stuff with dr dt and dH1 dt, and that's not good. We don't want that, right? You know, we're going to have two things in there. Why do we not want that? Well, because we don't know anything about dH1 dt, right? We only know all this is happening when h1 is 3 feet, so eventually we're going to use this, but we don't know what dH1 dt is, so that's going to be a problem for us. However, we do know dr dt. So is there something we can do to manipulate this equation before we take a derivative? So is there something we can do to this equation to get rid of h1 so that we only have r? And yeah, we could use this. So now this step is kind of just like in example 5, where we use the similar triangle equation here to get this volume formula in terms of only one of the variables. All right? So let's not take a derivative yet, because we can't, okay? Because we want to get rid of this h1 here. Okay, we want this entirely in terms of r, so that when we take a derivative, we only have dr dt in here. So let's use this equation to express h1 in terms of r. So h1 equals, just multiply both sides by 7, and then you get h1 is 7r over 5. All right, so that's good. Now we can take this, all right, we'll take this and stick it into here. So then v cone equals 1/3 pi r squared. Now what's h1? h1 is 7r over 5. All right, so let's zoom in a bit here. So now let's just simplify that a bit. So v cone equals 1/3 pi r squared times 7r over 5. That's going to be 7 pi over 15 times r cubed, right? So on the top we have 1 times pi times 7, so 7 pi, and then on the bottom 3 times 5, so 15, and then r squared times r gives us r cubed. All right, so that's great. Okay, that's the volume of the cone expressed entirely in terms of r. Now that's really good for us, that's great, because now when we take a derivative, what are we going to get? So let's do that now, let's take a derivative. dv cone dt equals 7 pi over 15. Now again, we've done this a few times already in the past few examples, but r cubed, r is a function of t implicitly, all right? Implicitly it's a function of t, and then we're going to raise it to the third power. So we have to do the chain rule to take a derivative. So chain rule says derivative of the big guy evaluated at the little guy. Okay, so 3 and squared comes from derivative of the big guy, and then r because we evaluate at the little guy, and then multiply by the derivative of the little guy. Okay? So that's good. And then we can simplify a little bit, I guess. 3 goes into 15 5 times, so that's just going to be a 5. So then dv cone dt, that's a d right here, dv cone dt equals 7 pi over 5 times r squared dr dt. All right, so let's zoom out a bit here. So how's that helpful? Well, now we can take this and this and then use those together. How can we use those together? Well, 25 pi dh2 dt equals dv sil dt, and this expression over here equals dv cone dt. And we know that negative dv cone dt equals dv sil dt, right? Because we got rid of this minus sign here, which, you know, in retrospect, I guess there was no reason I had to do that. You can put the negative sign on either side you want, but here we have it over here. So let's take dv cone dt, that's this guy. So we're going to take negative that. So negative dv cone dt is negative 7 pi over 5 r squared dr dt. All right, so this is negative dv cone dt, and it equals dv sil dt, which is this guy over here. It equals 25 pi times dh2 dt. All right. Okay, so again, negative dv cone dt, that's negative this stuff over here, equals dv sil dt, which is all this stuff over here. So this is much better for us because now, look what we have. Negative 7 pi over 5 r squared dr dt equals 25 pi dh2 dt. So, you know, we want dh2 dt, right? And we know what dr dt is, we're given that. But what's r? We don't know what r is. All we know is that this is happening when h1 is 3 feet. So we know h1, but we don't know r. Is there some way that we can use h1 to find r? Yeah, there is, using this equation up here, right? So h1 and r are always related by this equation here. So if h1 is 3, let's use this equation to find r. So zoom back in a bit. So if we go back to this equation here, then h1 is 3, and then 3 equals 7r over 5. So if we solve for r, then multiply both sides by 5 over 7, and then we just get 15 over 7 equals r. So when when h1 is 3 feet, then r is 15 over 7 feet, right? So now we have r, which we can stick into here. So now actually we're almost done. We have everything that we need to know to find dh2 dt. We know r now, and we know dr dt, so let's go ahead and plug those in. So what do we have? Negative 7 pi over 5 times 15 over 7. So it's r squared, so it's 15 over 7 squared. So let me write it like this. 15 over 7 times 15 over 7 times dr dt. Oh, sorry, dr dt, we know that, right? We know that. We're given that it's negative 2. Sorry, so let's just write that as times negative 2 equals 25 pi times dh2 dt. All right, so here, Negative and negative, when you multiply those together, you get a positive, so the negative signs cancel. That's great. 7 is going to cancel with one of these 7s down here. That's why I left them separately. 5 goes into 15 3 times. We're going to solve for dh2 dt, so eventually we divide both sides by 25 pi. So the pi's are going to cancel. That's wonderful. And then what do we have left? A bunch of stuff up here. Let's see. 15 times 3 is 45, times 2 is 90. So we have 90 over 7 equals 25 dh2 dt. So now we can just divide both sides by 25, and then we're going to end up with dh2 dt equals 90 over 25 times 7, which you can toss into a calculator or do mentally really quick. And anyway, that's going to be 18 over 35. And what are the units on that? Well, they're going to be feet per minute, right? Because if we go back up here, the radius of the water and the conical tank is decreasing at a rate of 2 feet per minute. So those are our units here, feet per minute. And you know, if the radius is in feet, then so is the height. And if the rate of change is per minute, then dh2 dt is also per minute. So that's actually pretty much it. dh2 dt is 18 over 35 feet per minute, which is about equal to 0.5143 feet per minute. All right, so this was a lot more involved than the other examples we looked at, you know, because we had a tank draining into another tank. So, you know, what happened here? We had these 3 equations we had to work with. You know, we wanted to find dh2 dt, and to do that we had to take a derivative implicitly of this equation. And to dv sil dt, we didn't know anything about that, but we know that it was related to dv cone dt by this equation here. Right? So then we found what's dv cone dt, and in order to do that, we had to get rid of the h1 out of this, okay? Because we only know dr dt. So that's why we had to get h1 out of here so that we can only have an r. So then when we take a derivative, we'll have dv cone dt equals stuff with r and dr dt. And then that's good because now we know dr dt, so we can take this thing we circled here, and this thing we circled here, set them equal to each other using this equation here, so we have a minus sign out there. And then we have to be careful because now we need to find out what's r, and we can find r using the similar triangle equation here, right? So there's a lot of stuff going on, and a lot of it's related to each other, and it might seem kind of confusing and pretty messy. And you know, it is at first, I guess, but if you practice with it more and more, it'll make more sense. And anyway, here's the answer again. And just a reminder, if you want to copy this worksheet, check the video description, and there's a link to download it. So that's it for example 6 with related rates.